Okay, so creating a confidence interval for a flu vaccine. Thomas Brooks, it is believed that 45% of vaccine eligible people received the flu vaccine, the results of a survey given to a random sample. That's important. Random sample of 2,350. So that's our sample size. N is 2,350. Indicated that 978, there's my X. X equals 978 of the 2,000. Oh, this is vaccine eligible people. And this is vaccinated people. Had received the flu vaccine. So they want us to do a 99% confidence interval. So with a 99% confidence interval, we have a Z star of 2.576. So we look at this. This 45% is our P, is 0.45, which means that Q would be 0.55. So let's create our confidence interval. Whoops, wrong side of the page. Here we go. So we find our P hat by doing 978 divided by 2350, 2,350, and that's 0.42, 42% of our sample. And so that makes Q hat of 0.58. Yeah, I had a lot of problems in writing these. So here we go. We have our information, our conditions, our calculations, and our conclusions. So under our information, P is 0.45, Q is 0.55, X was 978, vaccinated, 2350 is vaccine eligible, we found P hat and Q hat in our Z star. That's under our information. Okay, this was given to us, all this information to us is given for us at the beginning, or if we can find it by using what is given. The 42 was 978 divided by 2350. 0.58 was 1 minus 0.42 is 0.58. So then we look at our conditions. Our first condition is this, that was a random sample, because it says up here was a random sample of 2,315 vaccine eligible people. 2,350 is less than 10% of all U.S. vaccine eligible people, because we're talking about the United States in the paragraph, and later we talk about Canadians. So a random sample, less than 10% of our population of all U.S. vaccine eligible people, and then we find our success failures. 2350 times 0.45, 2350 times 0.55 gives us these two numbers, both much greater than 10. So we have more than 10 successes, more than 10 failures, random, less than 10%, all the conditions are met, we can do a 1 proportion Z interval. Because the conditions are met, we can do a 1 proportion Z interval. So that leads us to our calculations. We named 1 proportion Z interval, but we're going to go ahead and name it and claim it. We're going to go ahead and tell what the confidence interval is. It's P hat plus or minus Z star times the standard error. That is an S. That's not a 5 for all of you who can't read. That's standard error. So we have to find the standard error, which is, according to our formula page, the square root of P hat Q hat divided by N. So I plug my numbers in. P hat, remember, is 0.42. Q hat is 0.58. And N was 2,350. So plugged in, divided by, multiplied. We get 0.01012 dot, dot, dot. So I just went ahead, because of the 0101, I just called it 0.01. Which leads us to these numbers, 0.42 plus or minus 2.576 times our standard error, Z star, standard error, P hat, I just plug numbers in from what we're given, but my battery's low and I need to charge it. Okay, I'll do that in just a moment. Well, maybe not. It's already down. So I'm going to go ahead and show you this. Stat, go over to test. It's a 1 proportion Z interval. It's under A. I'm going to put my numbers in. 978, 2350. My confidence interval is 99%. And then I calculate. And I rounded those to 0.389, 0.38998. I made 39%, and the other one I made 44%. Which leads me to the conclusion we are 99% confident that the true proportion of vaccine-eligible people in the U.S. that were vaccinated falls between 39% and 44%. Let you pause on that for just a moment. So again, we start with our information. Make sure we put some context with that. Sorry, I didn't have it to begin with. Then we do our conditions of a random sample, less than 10%, and our greater than 10 successes and failures. I name the test. And even though I name the test, I then show the formula that goes with the test, how to find the interval, p hat plus or minus z star times the standard error. We had to calculate the standard error because we'd already calculated p hat up here. We were already given the z star because they told us it was a 99% confidence interval. Ran through my calculations, plugged it into the calculator and let it do it. And we get this, excuse me, we get this conclusion. Now, the next part of the question says, use your confidence interval to comment on the belief that 45% of the people had received the flu vaccine. Well, since 45% was not in our interval, I remind you the interval was 39% to 44%. I don't think the belief of 45% of vaccine-eligible people got the vaccine. Don't believe that because it didn't fall within our interval. Our interval was 39 to 44. It was 44.2, still not up to the even rounding to 45. So I don't believe that statement. Sorry, I needed to adjust that. Now that we've got that figured out, let's look at the bottom of the page. It says, suppose a similar survey was given to vaccine-eligible people in Canada. All right, then again, a 99% confidence interval will be receive the flu is to be constructed. What is the smallest sample size that can be used to guarantee that the margin of error will be less than 0.02? All right, so now notice they don't give us any numbers whatsoever except for the margin of error. Well, the margin of error is found by z star times standard error, which is p hat q hat over n. It's 99%, so we know z star. Z star is 2.56. Our margin of error is 0.02, so that's 0.02. If you're not given a p hat and a q hat, we always are set up to assume, yes, we assume that p hat and q hat are going to be 50-50, half and half. It's 0.5, 0.5. That way, if we have to find the conditions for this, say half the people are going to be, we don't have an n size, so we'd say half successes and half failures, make them equal. We're hoping that we're doing less than 10% of the Canadian population that's vaccine eligible. And it's less than 10%. Oh, excuse me, I've already said that part. And that we randomly selected them. Okay, so we're solving for n. We're trying to figure out how many people they're putting into this survey, this sample. So we plug in what we know, our margin of error, our z star, and p hat and q hat. Again, we're assuming they're half and half. Well, 0.5 times 0.5 is 0.25. We divide both sides. We're solving for n, so I'm doing a little algebra. I divide both sides, since they're multiplying, divide both sides by 2.576. 0.02 divided by 2.576 is 0.008. 0.2 divided by 2.576 is 0.00, it's really 0.0077 ... and a bunch of other things, but I rounded it to this because I knew what I was about to do. I had to square both sides. Why am I squaring both sides? Well, you square to get rid of the radical. Most of you can remember that from algebra. It's the inverse operation for finding the square root. You square it. 0.008 squared is 0.0005 and some change. And so I rounded that up to 6. Got rid of the radical. And that gives me 0.25 divided by n is this. So I move the n over by multiplying, and then I divide by 0.00006. N equals 0.25 divided by 0.0006. And that gave me 4,147.4. Well, we're talking about Canadians here. And while some of you may not have a high belief in Canadians, we're not going to have 4/10 of a Canadian. So we're going to round that up. Always round up to the next person because we want to get less than or equal to 0.002. So we need as big a sample as possible. So that's going to be 4,148 vaccine-eligible Canadians are needed to be sampled. 4,148. Again, it is an algebra problem. We set up to solve for n, plugging in what we know. They did not give us anything about p hat or q hat, so we're going to default to 0.5 for each, half and half. We can make that assumption and go from there. And so we should estimate, we should tell the Canadian health officials they need to have a sample size of 4,148 vaccine-eligible Canadians.